In February of 2023, an electronics designer opened an issue on an open-source icon repository. They pointed out a specific problem with the library's resistor symbol. It used the squiggly line instead of the international norm defined by IEC 60617. This request highlights a persistent fracture in how electrical engineers document hardware. North American engineering education often defaults to legacy regional symbols, while the rest of the world has adopted a strict, formalized international standard. If you studied electronics in the United States, you likely learned the IEEE and ANSI conventions. You draw resistors as jagged, zigzag lines, and you use uniquely curved, distinctive shapes for AND and OR logic gates. Under the IEC 60617 standard used globally, those unique shapes disappear. Resistors, logic gates, and integrated circuits are all rendered as uniform rectangular blocks. This creates immediate friction for engineers collaborating across borders. A schematic drawn in California can look entirely alien to a manufacturing facility in Shenzhen or a design team in Stuttgart, requiring mental translation to parse the logic. This discrepancy stems from a systemic push by IEC Technical Committee 3 to convert human-drafted art into machine-readable data. The International Electrotechnical Commission's Technical Committee 3, or TC3, governs the standardization of graphical symbols and technical information representation. Their primary objective is to phase out the historical practice of treating schematics as standalone artistic drawings intended solely for human eyes. Modern hardware design relies on electronic design automation software, enterprise resource planning systems, and automated manufacturing pipelines. These systems require structured, machine-sensible ontologies to verify connections, track inventory, and program assembly robots. A symbol optimized entirely for rapid human visual recognition, like a jagged resistor, becomes a severe liability in this environment. Complex, irregular geometry is computationally heavier to render and harder to map into a rigid, uniform database architecture. To see why this shift occurred, look at the history of logic gates. The familiar curved shapes were formalized by a 1960 AIEE and ASME task group, eventually becoming the U.S. Air Force's MIL-STE 806. This standard codified the exact geometry of the distinctive shield shapes we associate with AND and OR logic gates. A highly effective, human-centric design. A draftsman could draw them by hand, and engineers could instantly trace logic flows by recognizing their distinct exterior silhouettes. As digital logic grew exponentially more complex through the 1970s, custom shapes reached their operational limit. Designing a unique silhouette for every new, highly specialized integrated circuit became impossible. The industry began migrating away from the ANSI Y32.14 standard that maintained these shapes, seeking a more systematic approach. The solution was the IEC 60617 mandate, which forced all logic gates into a standardized rectangular block footprint. Instead of communicating function through an external outline, the standard relies on internal qualifier codes. Inside these identical blocks, specific typographic markers denote the operation. An ampersand signifies an AND gate, while a greater than or equal to 1 symbol denotes an OR gate. Embedding logic qualifiers inside uniform rectangles eliminates the need to maintain an ever-expanding library of unique drawings for every new logic function. The IEC rectangles act as scalable, modular containers for complex logic, rather than rigid, literal illustrations. We can see this codified syntax at work by analyzing a single complex component, the 4-terminal enhancement mode MOSFET. Even in North America, this symbol is governed by the strict rules of the IEEE 315/1975 standard rather than artistic preference. Constructed from a strict syntax of primitive elements, the vertical lines map to the physical silicon architecture, gate, gap, and channel. A broken channel line indicates an enhancement mode device, communicating the channel isn't continuous. A solid line represents a depletion mode transistor. Current can flow in either direction when the MOSFET is on, so the arrow doesn't indicate current flow. It's actually the standard primitive symbol for a PN junction, pointing inward to denote an N-channel substrate's intrinsic body diode, and outward to denote a P-channel. The IEE 315 MOSFET symbol functions as a codified schematic formula, mapping the transistor's underlying physics directly onto the page. This strict visual syntax enables IEC TC3's modern ontology frameworks, mapping the final step from human drafting to back-end database management. This relies on specific foundational data standards, primarily IEC 81346 for structuring systems and IEC 61360 for creating cross-domain data dictionaries. To achieve this, TC3 employs a bifurcated engineering approach, managing representations for both the human eye and the machine parser simultaneously. The human sensible representation consists of the IEC 60617 graphical symbols. The machine sensible representation operates entirely out of sight, governed by the IEC Common Data Dictionary. Placing a standard IEC symbol into an EDA tool triggers a background data event, linking the visual icon to a structured digital record. The visual rectangle acts merely as a mask for a background data pipeline. Placing the symbol generates a structured data parcel defined by IEC 62656, dictating exact metadata. This parcel assigns strict identifiers, like terminal designations from IEC 60455 and power supply ratings from IEC 61293, formatting them for enterprise systems. A uniform visual syntax guarantees that enterprise software can accurately parse the exact semantic class and lifecycle data of every single component on a board. This brings us back to the GitHub issue from 2023. The designer requesting the IEC 60617 rectangular resistor for their software library recognized the need for precise integration with an automated toolchain. The request was a strict enforcement of database compliance. A uniform component library is required to maintain the structural integrity of the design files. A single non-compliant squiggly line can introduce an undefined variable, corrupting the automated parsing of the schematic. Modern industrial schematics rarely consist of a single page. They are massive, interconnected digital architectures, mapping thousands of components. These schematics function as the foundational global data ontologies for all modern electronics production and supply chain management. In the modern era, these documents are read by ERP systems, robotic pick-and-place assembly machines, and diagnostic algorithms, just as often as they are read by humans. Mastering IEEE 315, IEC 60617, and TC3 frameworks is the critical threshold. It separates a designer who merely draws circuits from an engineer who architects scalable hardware systems.